Hello guys, welcome back. Today we are going to tackle a new problem called Kth Largest Element in an array. This problem will introduce to us a new coding interview pattern, which is the top K elements pattern. So basically, whenever you find a problem that says, "Hey, get the top largest K elements, get the minimum K elements, get the maximum K elements, get the most frequent K characters," or whatever. Whenever a question says get the most K something, you immediately think of that. You should immediately think of that pattern. Well, what is this pattern? This pattern is solved using a priority heap. Well, let's explore first the brute force way of solving this question. Well, let's first start by reading the problem statement. Find the kth largest element in an unsorted array. Note that it is the kth largest element in the sorted order, not the kth distinct element. Well, basically what that means is that, hey, the elements are not unique. So it could be, there might be a case where the array is 1, 2, 2, and 3. Well, the kth largest element, let's say k is equal to 3. The kth largest elements mean the third largest element in our case, which would be 2, not 1. Well, why is that? The first largest element is 3, the second largest element is 2, and the third largest element is also 2, because there is a duplicate of 2. And so yeah, that's basically what that means. So the first approach that you could think of is, hey, let's just sort the array in a descending order, and then just get the kth minus 1 index. Well, why is that? Well, because when we sort the array in descending order, the first element would be the largest one, the second one would be the second largest one, and so on and so forth. And getting the kth minus 1 index is because k starts from 1 while the indexes starts from 0. So to do that, we would need the sort the array, which is a primitive type in Java. So doing that in Java is kinda not direct, but if you actually want to do that, you could just implement your own merge sort algorithm, or just sort the algorithm in ascending order, then reverse it, because sorting primitive type in descending order in Java is not built in. So what I'm going to do is just convert it to a list of integers, not a int primitive type. So to do that, it's pretty complicated. It's sort of complicated, and it's out of scope of the video. But if you want to read about it, just read about streams and why I need to do that. So let's just say arrays.stream nums dot boxed dot collectors dot to list. Okay, so what that basically does is get the number primitive types, int primitive types, box them into a stream of integer, and collect that stream of integer into a list of integers, which basically what I need. So collections dot sort that array, and collections dot reverse order. So by doing that, we have an array list of integers that are sorted in descending order. So let's just return array.get k minus 1, and in the problem statement it says that you may assume k is always valid. 1 is less than k, k starts from 1 and is less than the array length, so we don't have to validate that k is less than nums.length. So let's just run the code. Okay, it works. Let's just submit it, and it works. 6 milliseconds faster than 40% of Java online submissions. Well, this isn't the most brute force approach, is still bad. Well, why is that? Because sorting is n log n, and as I said before, a the sorting approach is not the worst approach. It's not the most brute force approach, but there is better, and there is a more of a pattern that could solve a lot of questions that says get me the kth something, the kth most get me the top k elements in something, the most frequent k elements, the most duplicate k elements, the most largest k elements. So to do that, we are going to need a priority heap. Well, why is that? Okay, so let's first start by defining what a heap is. Well, a heap is basically just a complete binary tree. And at that point, you would ask, what is the difference between a binary tree and a complete binary tree? Well, the difference is in a complete binary tree, you can't do something like this. But actually, in a complete binary tree, you have to fill all the levels left to right before actually having the ability to go to the next level. So what you basically need to do is like this, this, and this before actually going to the next level, let's say here. And you have to fill them left to right. You can fill here, then go here, then so on and so forth. So what makes a heap special is not it's a complete binary tree, but something else actually, is that let's say we have a minimum heap, which is a type of heap. In a minimum heap, well, actually what you have is that the node's value, let's say the node's value is 1. Okay, so in a minimum heap, all the children of that node must be of a larger value than 1. But unlike the binary search tree, the heap doesn't have a structure, doesn't have a hierarchy. So meaning that this can be 2 and this can be 3, or this can be 3 and this can be 2. It doesn't matter. So there is no hierarchy like in the binary search tree, where the left value must be less than the node's value and the right value must be more than the node's value. No, there isn't a hierarchy here. Just have to be larger than the node's value. And in the inverse case, where you are using a maximum heap, which is another type of a heap, the children of a node must be of a less value than the node's value. So if that was a maximum heap, 3 would be here and 2 and 1 would be here. Okay, so what is the time complexities of the binary heap? Well, let's say the reading the minimum value, in our case this is a minimum heap, so getting the minimum value, getting the most minimum value of a set of numbers, or if of an array of numbers. So getting the minimum value is basically just O of 1, because a binary heap, a minimum heap, promises us that the first node would always have the minimum value of a set of numbers, okay, or an array of numbers, or an interval of numbers, whatever you want. So basically it means that the first node would always have the minimum value of all of these values. So reading the minimum value is always O of 1, which is actually a special thing about the heap. Also, a heap could contain duplicates. Unlike the binary search trees, they can't contain duplicates. So how does it promise us that the first node would always have the minimum value? By doing something called a heapifying operation, which is fixing the heap. So let's say we have added a node here with a value 0. Well, after we add the value 0 here, well, our first node isn't now the minimum. So what we have to do now is just heapifying the structure, making it a heap again. That's where the name comes from. So what basically happens, and I wouldn't go into implementation details, if you want to do, you can just look it up yourself, but this is out of scope of the video. So what basically happens is that node comes to be the first node, and these nodes are fixed accordingly to what the the exchanging of nodes need. So basically this node goes up a level, then goes up a level, and this goes up a level, and all the corresponding nodes that needs to be fixed due to this operation would be also fixed. So going up a level, up a level, up a level is basically going through the height of the tree, height of the heap in our case. So the height of the complete binary tree is O of log n, because it's a balanced binary tree, and the height of a balanced binary tree is log n. So basically you are doing O of log n operation to insert, and basically the delete is also the same. Let's say we removed 1 and 0 isn't here anymore. Let's say we removed 1. Well, the next minimum element is 2, so let's heapify the structures to make 2 as the first node. So this is also O of log n at the worst case, and extracting the minimum, meaning removing the first node. Deleting could be any of those nodes, but extracting the minimum means deleting the first node and fixing the heap accordingly, which is also gonna be O of log n. Well, okay, so how can we solve our problem using a heap? So the basic intuition, well, hey, since the first element always contains the priority, the most element that has a priority to us, well, why not fill the heap with the priority that we want, and just extract the kth element as our return value. So what I mean by this is, hey, like there is a minimum heap, we can construct a maximum heap. We could construct whatever priority we need as a heap, where actually a heap is conceptually called a priority heap because you set your own priority. So let's say we use a maximum heap with values like 1, 2, and 3. Let's say our array is of values 1, 2, and 3. Well, a maximum heap, like I have discussed before, is that the first node is the most maximum one of these, of a set of numbers or an array of numbers given. So what basically happens here in a maximum heap is like 3 and 2 and 1, and this could also be 3 and 1 and 2. As I have said before, the hierarchy of left and right doesn't matter in a heap. So if we do as we said, let's just extract the kth elements, as we need the kth largest element. So let's say k is equal to 2, which means in our problem that we need the second largest element. Well, the second largest element, we would get to the second largest element by extracting the first largest element, and then the heap will automatically heapify the structure, making 2 as its first node, so it becomes something like this, 2 and 1, once we extract the first largest element, and then we would just return the extraction of that resulting heap. So we would just return, hey, let's just return the extraction of that heap, or just peek, or just read the value of the top of the heap. So this is our result. Well, this is actually not any better than a sorting algorithm. Well, it could be worse than a sorting algorithm. Well, why is that? So as we said before, insertion is of log n complexity. Insertion is of O log n complexity, and we have n elements. So basically, filling the binary heap is of n log n cost. And unlike the list of after sorting, we could just get the kth element by index k-1, because lists have a random access property, where you can access any element if you know its index. But here you can do that. You have to extract you have to extract the top node, and then do the same until you get to the element that you want. You can just search through the binary heap. That's not how it works. So actually here we would need to extract k elements to get to what we want. So this is basically k of log n. So instead of here in the list approach, in the sorting approach would be O of 1. That section would be O of 1 because it's a random access operation, while here you need to extract k elements to get to the result. So, well, this is asymptotically equivalent to the sorting approach, but it's actually worse. So what we can do here is just explore the problem. Well, let's say we have 1, 2, 3, and 4. Okay, 1, 2, 3, and 4. Well, what are the two, if our k is equal to 2, what are our two largest elements? Well, our largest elements would be 3 and 4. Okay, that's all nice and good, but how can we get them at the end of our iterations? So let's say this is the end of our iteration, and I want that answer to be the end of our iteration. Well, we could basically do something like, hey, let's assume an answer. So here and here, let's assume that our answer is the first k elements. It could be. So in a situation like where we have like 3, like we have 4, 3, 2, and 1, if we assume that our answer is 4 and 3, we would actually be correct. But in our case here, we won't be correct. Well, our assumption would be 1 and 2. Well, that's not a correct assumption, but we have two elements, so, and our case too. So we are saying, hey, let's assume that the first k elements are the answer that we are looking for. And bear with me here, all of this will make sense in a moment. So our answer is basically 3 and 4. Well, here at 1 and 2. Okay, which one of them could be the most wrong one, or have the probability that it is actually an incorrect assumption? Well, what if we have 1, 2, and 3, and we need the k largest elements? Let's say k is equal to 2 also, so our assumption would be 1 and 2. Which is the same step as here, but different elements, 1, 2, and 3, and while here is 1, 2, 3, and 4, which changes the answer. So here, what if we remove the 2? Okay, so what if we remove the 2 so here we made the assumption by going 1, 2, and now we are at 3. So what if we remove 2 and put 3 instead of it? Well, is that the largest two elements? No, it wouldn't be the largest two elements. Well, actually the largest two elements are just 3 and 2. So probably our incorrect assumption would be the minimum of the two of the set of k numbers that we assumed, because with the minimum of them, well, we assume that set of numbers are the largest set of numbers in an array. So if the minimum of them, which is 1, is correct, then the larger ones are also correct. So let's say in the example we said before that the array is 4, 3, 2, 1 instead of 1, 2, 3, and 4. Well, the largest elements would be 4, and 3, which is our assumption. Well, what is the minimum of the two? The minimum of the two is 3. And when we get to 2, we are going in reverse. When we get to 2, hey, is 2 one of the answers? No. Is 1 one of the answers? No. Well, what do we compare 2 with? Well, we compare it with the minimum of our assumption, because if minimum of our assumption is correct, is valid, then the larger ones of our assumption are also valid. So basically what we are doing is, hey, so let's assume an answer, and let's assume an answer that this answer is the maximum or the largest numbers, and let's compare the rest of the numbers with the minimum of our assumption. And if our assumption is correct with the minimum value, then all of the other values in our set of numbers would also be correct. So what if that didn't happen? Like here, 1, 2, and 3, let's say this is 4 also. Well, what would happen if it's not correct? Well, when we go to 3, let's remove 4 for now. When we go to 3, well, is removing 2 a valid choice? No, it's not, because 2 could still be part of the answer, while actually the minimum one has the most probability of being the wrong one. So why not just remove 1 and put 3, which is the more valid answer that we have at this iteration? So it becomes like 3 and 2. Well, 3 and 2 is the correction of our assumption at that iteration. So let's go to the next iteration. Well, at the next iteration the array is finished and we have our answer. Okay, so let's trace this here, and 1 and 2, and now we are at 3. Let's do the same, get rid of the minimum one and put the maximum and put the more correct value. We compare each value with the minimum one of our assumption. So 3 is 3 bigger than 1. Yes, it is bigger than 1, then our assumption is wrong, but the rest of the assumption, rather than the minimum part of our assumption, could still be correct, because we need k elements, not just the largest element. So let's remove 1 and make it a 3, so it becomes 3 and 2. 3 and 2. Okay, so now we are at 4. Well, at 4, is our assumption correct? No, it's not. How did we know? Because we knew because 4 is larger than our minimum. Well, why not choose 3 to exchange 4 with? Well, because 3 could still be part of our solution, but we are sure that the minimum one of our assumption, if it is incorrect, then it's the one that should be exchanged with the more correct value that we now have. Well, what if the rest of the values are also incorrect? Well, they would be the minimum at some point of the next iteration. So if we found a larger one, they would get extracted, they would get exchanged as a result of that. So here 3 and 2, well, let's just compare it with 2, which is the minimum of our assumption. No, it's not larger, so 4 is larger, 2 is not larger, so let's say 4 is here. So our answer in the end is 3 and 4, which is the correct answer. Well, let's see how we did that. Well, how we did that is actually comparing the minimum of our assumption each time. Well, how do we get the minimum of a set of numbers each time? We get it using a minimum heap. That's why the problem is solved using a heap, as I said before. Well, why is this any better? Because the actual heap would be of height log k. Why log k? Because you are just maintaining a heap structure. Notice that our assumption is just k elements. So k, if k is less than n, so the heap structure would be of a height less than if we filled the whole heap with n numbers. We would just fill it with k number and just maintain that structure along the way. So what we actually are doing is getting the minimum each time at an iteration. So basically we are just saying, hey, our assumption is 1 and 2. Okay, what is the minimum value? Well, the minimum value is 1, and we are at this iteration we need to put 3 instead of 1 because of the things we said, that 3 is larger than the minimum value of our assumption, and our assumption is the largest value. So basically what we need to do is exchange these numbers, remove 1 and put 3. So what we are going to do is like here, put 3, so and the heap heapifies the structure, fixes the structure so that the next minimum element is the top of the heap. So now we have 2 and here is 3. Well, our minimum is 2. So when we get to 4, well, what is the minimum that we have? We have 2. Okay, so let's just remove the minimum and put the next larger one at that iteration, so it becomes 3 and 4. And basically this is our answer. Well, are we done? Well, actually there is one little more operation. What if the problem said that, hey, I need the answer to be in a sorted order? Well, actually not most questions do, but something that I forgot to mention, that a binary heap or any type of heap isn't sorted. It just promises you that the top element would have a minimum value. In case of a minimum heap, would have the minimum value of a numbers, and that element would have a minimum value of its subtree, and that element would have a minimum value of its subtree, so on and so forth. That value would be minimum of its subtree, which is basically the whole tree. So it doesn't promise you that when you iterate on it, it would be of a sorted order. So returning the answer as a sorted order is not quite straightforward. So we would start with the saying, hey, the sorting isn't important. Let's say I need the k largest element, I need the 2 largest element of the array, but the sorting isn't important. I need 4 and 3 or 3 and 4, both are correct to me, they are the largest elements. So to do that, there's a built-in method in Java that just converts the heap into a array, which is our solution. But what if we want to just get 3 then 4, not 4 and 3? We need to maintain that actually we need to get 4 then 3, because we need to maintain the largest hierarchy, meaning the largest one, the second largest one, the third largest one are in a sequence. So well, here, well, let's notice that we have k, which is the length of our assumption, which is also the length of our answer. Let's say we need the answer as an array. So let's say the array is of length k, meaning 0 and 1, and that array is initially empty, or in our case filled with zeros, because it's an int array. If it were objects, it would be filled with nulls, because Java fills them automatically. So we need here 4 and we need here 3. Well, how can we do that? By extraction. Well, by extraction, if we extract the first element, put it here, it would be 3, and we then extract the second element, it would be here 4. So this is not our answer. We could do that and just reverse the array, but this is a bad complexity. So let's do the more smarter thing, which is, hey, let's start from the end of the array. Let's fill the array from the end. So hey, we are at the end of the array. Let's extract the first element of the heap. Well, the first element of the heap is 3. Okay, let's go to the next element until we reach after 0, which is the negative value in a loop, I mean. So in 0, we would just extract the next value from our minimum heap, which is 4. So now we have 4 and 3. So now you have your algorithm, or you have your time complexity as, so making our assumption is k log k, because basically what you do is get the first k elements, okay, get the first k elements and put them in a heap that you would maintain its structure as of a height of log k, because the heap would always have k elements only. You wouldn't fill all the numbers. No, you would maintain the heap by just removing the minimum each time and putting the more correct answer. So k log k plus, well, you would need to loop on the rest of the array to correct your assumption, to validate your assumption or correct it. So what are the next the rest of the elements? Well, it's n minus k also log k, which is actually equal to, well, let's just write it first, n minus k log k, and all of this is actually equal to n log k. Why is that? It's because k is a subset of n. K is always less than n, and we eventually loop on all the elements, so basically it is n log k, which is far more better than n log n. And what if we just want to get the elements in a sorted in not a sorted order, meaning just convert them into an array? So that is an n operation, which is asymptotically still equivalent to n log k. What if we would needed them sorted in a array by doing the approach that I have just discussed? Well, it would be still n, so still asymptotically equivalent to our question, our asymptotically equivalent to n log k, which is far more better than n log n. So in our question, it needs only the kth largest element, not the k largest element. So it doesn't need the two elements, it just needs the kth largest element. So maybe the second largest element, where, well, here, where is the second largest element? Well, the second largest element is 3, which is the top. Well, what if we had a heap of numbers and we need the second largest element, like in the first example? Let's say we made a minimum heap with 1, 2, and 3. Well, 1, 2, and 3, and we need the kth largest element to be the third largest element. Well, the third largest element is 1, and here the second largest element is 2. Since we always keep the height of the tree, or the total number of elements in the heap, to be k, and we made it a minimum heap, meaning the least largest element, the minimum element of our heap, is the top node, is the first node. And since we assume that our minimum heap is the largest elements, so basically by constructing a maximum heap using a minimum heap, which is what we did here, the minimum largest element would be the first node of that heap, would always be the minimum element, would be the top element of that heap, and it is our kth largest. So all we need to do is just read the kth largest element, which is here 1, and the kth largest element, which is here 3, and just read and return it. So reading and returning it is O of 1 complexity, because as we said here, we just read the value of a node. It's a constant time complexity, the first node. So our asymptotic complexity is n log k, which makes it far more better than n log n plus k log n in the case of a maximum heap, and the sorting approach, which is n log n. So basically, to summarize, what we have to do in a top k pattern problem is to do as follows. Hey, what does the problem actually need? It needs the top k largest elements. So let's make an inverse context of that context. So our context is largest. Let's make an inverse of that. Let's make a minimum heap, the inverse heap of that context, and just make an assumption and validate that assumption, correct that assumption along the way by seeing, hey, is that value that we are currently on bigger than the minimum value of our assumption? If so, just remove the minimum value and put the larger one, because the rest of the numbers could also be in our final answer. As we said before, if they are not in our final answer, so if we have 1 and a 2 and we have 3, well, 3 will replace 1. What if 2 wasn't the part of the answer? What if there exists a 4 and we need the 2 largest elements? Well, eventually 2 would be 2 of our assumption would be the minimum at a point in time. So whenever 2 is the minimum, it would get replaced by the larger one. So whenever we get to 4 here, well, 4 at the point that we are at 4, the minimum one of our heap is actually 2. So we say, hey, is 4 less than 2? No, it's not. Is 2 bigger than 4? No, still it's not. Then just exchange that. And we made sure that the rest of the elements are larger than the one we are comparing against, because it's a heap structure. Okay, and heap promises us that the first node is always um, the most priority, the one that has the most priority to us. So in case of a minimum heap, the first element is the minimum one. In case of a max heap, the first element is the max one. So that's the pattern. The patterns are very important to coding interviews. They basically solve the يعني, a set of problems. There are a lot of problems that have that pattern underneath it, like as well as other patterns. So basically understanding the pattern, basically how knowing how to approach the problem and why, saves you a lot of time. Instead of answering a lot of questions, you just know the pattern, and whenever you find a question of that pattern, you would just solve it easily because you already know how to solve it. So, and we would prove that in a moment. And I think I would answer. I will answer a question that I haven't seen before, that is of the same pattern, and do the steps that I have said, and eventually I will solve the problem, and we would see that. Okay, so let's get to the problem. A priority heap in Java is implemented as a priority queue. So let's say queue of integer is equal to new priority queue of, well, whatever, and we would just say, hey, let's fill the priority heap with elements till k. So int I is equal to 0 till I less than k plus plus I, and I didn't I didn't give it a name. So let's say it's minimum heap, because it's a minimum heap by default. And what we would do is min heap dot add nums of I. So now we made our assumption. We basically did this step. Okay, and just, hey, let's validate it and correct it along the way. For int I is equal to k, I is less than nums.length plus plus I. We would say, hey, is the element that we are on larger than the minimum of our minimum heap, which means the top of our minimum heap? If so, just remove our minimum from the minimum heap and put the number that we are on, for the reason that I have just discussed with you. So min heap dot peak. Okay, if so, just do a minimum heap dot remove and a minimum heap dot add nums of I. So what that basically does is, like here, okay, it's 3 less, is 3 bigger than 1? Yeah, okay, so remove 1 and put 3 here, because 2, which is the larger number, or the larger set of numbers than our minimum number, could still be correct, could still be valid, along with the number that we just said, hey, it's larger than the number we have. So let's just remove the most the number in our assumption that has the most probability of being false or being incorrect, and just swap it with the number that we are on now, which is in our case the minimum number, and just return in the end minimum heap dot remove, since it just wants the kth largest element, not the k largest elements. So it just need this, not 3 and 4, for instance. So, and by the end we would have 3 and 4 because it's a minimum heap. And just let's run this, and it works as expected. Let's submit, and it works basically twice faster than the sorting approach. That's it for that question. As I said, it's a pattern that could solve a lot of questions using the same approach, the same way. It's in coding questions, it's all about patterns, not just solving a lot of questions, but understanding the pattern underneath it, the approach that you should take in case of something happened. So let's prove that. Let's go to a similar question. K closest points to origin. Well, I haven't solved that one before, so let's explore it together. We have a list of points on the plane. Find the K closest point to origin, 0 and 0. Here the distance between the 2 points on a plane is the Euclidean distance. Well, I don't remember what Euclidean distance is, so let's just search for it, as you should if you tackle a problem that you don't understand something. And I basically remember it, but I want to make sure that I know the format in a correct way. So yeah, basically P1 and P2, Q1 Q2 x2 minus x1 all power 2, and Q2 minus P2 all power 2, which is y2 minus y1 all power 2. So let's just do that. What we want the K closest points to origin, so let's trace the example. Sorry, you may return the answer in any order. The answer is guaranteed to be unique except for the order that it is in. So basically what it tells us, hey, return 4. Well, in the previous question, what it means that, hey, return 3 and 4, or 4 and 3. Just basically gets me the top largest K numbers. So here in this question we would get the K closest points to origin in no sort, but the K closest ones. So here K is 1, which means get me the closest one. So 1 and 3 with the origin, meaning 1 square minus 0 square, 1 square plus 3 square, because origin is 0 and 0. So what that basically is square root of 1 times 1 plus 3 times 3, which is 9, which is 10, I mean. So square root of 10. And here the other one is square root of 8. Well, the closest one is square root of 8. So we don't actually need the square root. The square root of a last number would be the less value. Yeah, we don't even need the square root. So the answer is just negative 2 and 2, and here the same happens. So we basically need, since here we need the closest K points, what we are going to do is get the inverse, make a priority queue of the inverse of that context, which would be the farthest points. Well, how are we going to do that? Let's just first start with making an int array priority queue, which is going to be farthest points, which is going to be equal to priority queue. And let's just trace that. Sorry, as I have said, I haven't solved this one before. So basically what I'm going to do is assume the question like I did before. So for int I is equal to 0, I is less than k plus plus I, farthest points dot add. Well, we would need to put the array itself. So points of I, and then for int I is equal to k, sorry, and I is less than points dot length plus plus I. What we need to do is that, hey, is the point we are on closer than the minimum farthest one? If so, just exchange it. So if if um distance of points of I less than this distance of farthest points dot peak, if so, just remove farthest points dot peak, which is just remove, and farthest points dot add just the point of I. Sorry, points, and here it's point. Yeah, okay. And in the end, it says that we don't want to get them in any order, just return them in any order you want. So farthest points dot, which is now our correct elements to array of to multi-dimensional array, which is a new int array of of k, because the answer is of k. Okay, so now what we need to do is implement the distance algorithm. So let's say it's a boolean, and let's just say distance, no, let's just say int, sorry, and it would just, as we said, we don't need the square root, because a square root of a larger number would be less than a square root of a smaller number, and it would take an int array point, with point of 0 being the x-axis and point of 1 being the y-axis. So it would just return point of 0 times point of 0 plus point of 1 times point of 1, because it's with the origin, so minus 0 is the same as just not including it. So let's just try to run it. Okay, k is uppercase, so let's convert it to a lowercase one. Wait. I cannot be cast to class line comparable. Oh, sorry. I need to wait, what? Oh, sorry. It needs a comparator. So what I can do is just say A and B, where A and B, each of them is an int array. Okay, so we would just need the smaller distance. So yeah, integer dot compare the larger distance, integer dot compare distance of B with distance of A. So let's try that, hope it works. Yeah, it works, so let's try to submit it, and it does, and its runtime 16 milliseconds, faster than 75%. So yeah, as you can see, it's the first time I try to solve it. So yeah, this is what coding patterns mean. It means, hey, you just get the basic idea behind the question and you just implement it on different coding questions, because you get the basic idea. And yeah, that's about it. To explain this part, well, a priority queue in Java an if it's not a object of not being an array. So whenever you use an array as an object in a priority heap or a priority queue in Java, you have to give it its own comparator. So basically what I did here is, hey, for using a lambda expression, making an anonymous object of that comparator while implementing it. A is an int array, B is an int array, integer.compare, which is a built-in method that is needed or should be used while making a comparator or constructing a comparator, which you can look up yourself if you want. It's out of scope of the video. Distance of B and distance of A. What that basically does is sort them in descending order, which is what we need. We need the farthest points. So the farther point would be the top of the priority queue. That's about it. So thank you for watching, and I hope you have learned something out of this video. I know it's a long one, but I hope that it'll give you an idea of what coding patterns are and why they are useful more than solving a lot of questions. Thank you.